Yeah. So this is a continuation of the Laplace transform of the functions we have been doing before. So I've covered this the function, the transform of these functions, this of a constant function, of the powers of t, and of trig functions like sine of kt, cosine of kt. So I've treated these three functions in my last three videos. So you can go back to check the other videos on the transform of these three functions. Now we'll be doing this today. So we learn how to find a transform of e raised to power 80. That will be today's topic. So which is the fourth part, Laplace of e raised to power 80. But we know from the definition that so let me take it as a question. As a question, that will be the find Laplace of what? Of e raised to power 80, where a is an element of real number. It can be any number whatsoever, any real number whatsoever. So to find out from the definition of Laplace, that should be equal to the 0 to infinity of this function multiplied by e raised to power st, and you have your what? You have your dt. That is the definition of what? Of Laplace. So it is a function times e raised to power minus st. Then you integrate it from 0 to infinity dt. That's the transform of any function. Any function whatsoever. Just take the function, put it inside here, and have the e raised to power minus st, and integrate it from this boundary from 0 to infinity. So what you just do next is, now looking at this, in my other videos, something like this, I've used this in a very simple way, in the sense that this looks like what, like an indices where you can add up the powers. So yeah, that becomes minus s minus a t dt. How did I get out? We know from indices, a raised to power indices. Indices, we have a raised to power m times a raised to power n is equals to a raised to power m plus n. So you can add the powers of both of the same base, which also happens here. This is e and this is e. So you can add these two together. So I added at plus minus st, and that is at minus st. Are you getting? So what I did is, there is t is common here, and I also took a minus outside. Taking the minus outside, you have s minus a, and I have what? T. When I expand this, you go back to this. Let's try it out. Expand this, that is minus s plus what? Plus a, and you have a t here, and that becomes what? Minus st plus at, which equals to what is here. Can you see? Can you see that it's equals to what? Equals to this. So this expression here and this expression here, they are what? They are equal. So that takes us to this. To make the integral easier, I want to continue from there. To make the integral easier, what you can do is just make a substitution to reduce it. So for that, you can say, okay, let k equals to that. Let k equals to s minus a. Are you getting? And from there, so you know that from differentiation, um, s minus at, sorry, I want my k to be s minus a multiplied by t. Then from there, my decay dt will be equals to I don't I can continue from here. I can say okay, my decay dt should be since this is t, so differential is what is x minus a, s minus a. That will be the differential of this decay dt, because I differentiating to respect to time and to respect to t. So your dt here, taking this dt here will be equals to decay over s minus a. From there, so you can replace what was here before as Laplace of e raised to power at equals to 0 to infinity of e raised to power minus s minus a multiplied by t dt. Everything here becomes e raised to power minus k, and here becomes this whole expression k is equals to s minus at. I place everything here by k, and the t here is equals to decay over this, so that is decay over s minus a. So this gave us 1 over s minus a, and that gave us 0 to infinity of e raised to power minus k decay. So you can find the integral of this of e raised to power minus k decay. Though for my last videos, the integral of this is equals to 1. For my last video, integral of this is equals to 1, but to just for proving sake, I have to prove it again. So proving that, I have 0 to infinity of e raised to power minus k decay. I can say okay, this now the integral of this is equals to e raised to power minus k over minus 1. You can take from boundary from 0 to infinity, like from 0 to infinity, and that way. So let me take the minus 1 out first. So I have e raised to power minus k from 0 to infinity, and this can be written as e raised to power k from 0 to infinity. So that gives us minus 1. That gives us 1 over e raised to power infinity minus 1 over what? E raised to power 0. So that gives us minus 1 over infinity minus 1 over 1. Guys, and we know 1 over infinity is 0, and this is what? 1. And 0 minus 1 is minus 1 times 1, that is what? That is plus 1. So this integral itself is equals to 1. Therefore, Laplace of e raised to power 80, which is equal to 0 to infinity of e raised to power 80 e raised to power minus st dt, which I then transform to become this. So following this proof, I'll be using this result in my answer lead down. So I know this gives me 0 to infinity of what? Of the e raised to power minus k that is substituted in the last place, and here also become the k. I brought out this 1 minus sa I've done all this before. I'm just trying to rewrite it again. This gives us 1. So that is 1 minus SE times 1. And your answer is equals to 1 minus SE. That will be your answer. So that is the Laplace of e raised to power 80. So in the next video, I'll be doing a video on how to take the Laplace using different theorems, like the first shift theorem and other theorems. But for now, this is our answer. So generally, Laplace of e raised to power 80 is equals to 1 minus SE. That's the answer for that.